Hello and welcome to EduSathi. Let's continue the topic of geometry. Now we'll be moving towards circles. We have already done triangles, quadrilaterals and polygons. Polygon was a figure that has n number of sides. Now if I extend the number of sides to infinity, I get a circle. So circle is a polygon with infinite number of sides. Let's look at the definition of a circle. A collection of all the points in a plane which are at a fixed distance from a fixed point in a plane is called as circle. The circle is basically the collection of all the points, which is the circumference, and there are infinite number of points that I can have on the circumference which are at fixed distance. That fixed distance is radius. Every point on the circumference of the circle will be at an equal distance from the center of the circle, and that equal distance would be the radius of the circle. In the figure given to you, O is the center of the circle. This line is representing the circumference of the circle. The shaded region refers to the area of the circle. A line passing through the midpoint of the circle, or the center of the circle I should say, is known as diameter. And half of the diameter is your radius. So let's look at it. If you have 3 points, you can only draw one and only one circle passing through the 3 given non-collinear points. To two non-collinear points, you can draw a line. Minimum number of points that you require to draw a circle is 3, and all 3 points should be non-collinear. As already stated, diameter of a circle is twice the radius. Radius is from the center to the circumference. Diameter is double that of radius. A line joining the 2 points on the circumference of the circle and passing through the center of the circle is known as diameter. Circumference. Circumference is basically the perimeter of the circle. Circumference is the length of this boundary of the circle. So circumference is the length of boundary, and it is given by 2 pi r. So if you open the circle, if you cut out the circle at one point and open it into a linear thing, the length of the y or the length of the line would be equal to 2 pi r. Area. Area of the circle is given by the formula pi r square, where r is the radius and pi equals to 22 by 7. The value of pi can also be taken as 3.14. Which value you will take will depend upon how is r given to you in the question. Let's move ahead and let's look at a circle, and let's look at 2 points on the circumference of a circle. So I've taken randomly 2 points P and Q on the circumference of a circle. Now what is happening, this P and Q, if I cut open the circle at this point, these 2 points, what will I have? I will have the circumference or the perimeter of the circle divided into 2 parts. One is this line PQ, another one is the smaller PQ. Now the bigger PQ is known as the major arc. So this PQ that I will have starting from here, go on till this, will be known as major arc. It is a arc that I have. And the smaller distance between PQ on the circumference of the circle will be known as minor arc. I can find out the length of the major arc and the minor arc. However, if I look at major arc and minor arc, they will always add up to give me a value which is equal to circumference of the circle. And circumference of the circle is given by 2 pi r. Now if I look at it, if I look at the length of the major and the minor arc, the total angle at the center is 360 degree or 2 pi. 2 pi angle, this angle I am talking in radians, 2 pi angle gives, if I talk about the total angle, 2 pi gives me a length which is equal to 2 pi r. So if I talk about 1 radian angle will give me a length which is equal to r. And if the angle which is there at the center is theta radians, the length of the arc will turn out to be theta into r. The only thing that I have to take care is this theta angle which is there is in radians. If I have to convert it into degrees, I will convert radians into degrees. How I'll convert? 2 pi radian is equal to 360 degrees, or pi radians is equal to 180 degrees. So I can follow the formula. 360 degrees gives me a length which is equal to 2 pi r. Theta degree will give me a length which will be theta over 360 into 2 pi r. So if I look here, I can find out the length of the minor arc PQ. Similarly, I can find the length of the major arc. The total length that I have is 2 pi r. If I subtract theta r, which is the length of the minor arc, the length that I'll be left with would be 2 pi r minus theta r. R can be taken common and the value that I'll have will be 2 pi minus theta. Now what is this 2 pi minus theta? 2 pi is the total angle out of which theta is subtended by the minor arc. So the major arc, the angle that it will be subtending at the center would be equal to this total angle which is 2 pi minus theta. So it will be 2 pi minus theta into r. That will be the length of the major arc that I have. The other thing that you should understand is the word sector of a circle. Now if I look at it, here PQ, I was talking about the arc. This was the minor arc and this was the major arc. Now if I join the two endpoints of the arc with the center of the circle, so if I join this and if I join this, I get a thing which is this total thing, which is POQ, which is like a part of the circle. This is what is known as sector of the circle. So sector basically represents part of the circle and it has to be from the center. It's like you have a round pizza and you cut it into 6 or 8 equal parts. Each part is known as sector of the circle. It is always from the center. I can find out the perimeter of this and I can find out the area. First, let's look at the perimeter. Perimeter would be this length of the arc, which I have already calculated, plus if you talk about this radius and this radius. So length of the arc in degrees is given by theta by 360, which is the angle which is there at the center, into 2 pi r. The one that we have solved here, theta by 360 into 2 pi r is the length of the minor arc, plus this radius and this radius, which basically forms the two sides of the sector. So this will be for the sides and this will be for the length of the arc. This is same as this. Here this theta is in radians. If I convert it into degrees, it will be theta by 360 into 2 pi r. If I have to find the area of the sector would again be given by the same formula. If the total angle which is subtended at the center is 360 degree and the area of the circle is pi r square. If the angle subtended is 1 degree, it will be 1 over 360 into pi r square, or pi r square by 1. If the angle is theta degrees, it will be theta over 360 into pi r square. So it's a simple application of unitary method to find out the area and perimeter of the sector of a circle. The other thing that we need to understand is segment of a circle. Segment. Now instead of joining the two endpoints of an arc with the center, if I join them with a line. Now what is this? I have a line PQ. This shaded region that I create now will be known as segment of a circle. If I join it with the center, I got the sector. If I join it with a straight line which is not passing through the center, the minimum distance between the 2 points P and Q, the shaded region that I get is known as segment of the circle. So you need to differentiate between the sector, which is the two endpoints on the arc joined with the center, and segment, the two endpoints of the arc joined together. Perimeter of this sector, perimeter represents what? Perimeter is equal to the length of the boundary. So it will be equal to the length of PQ, which we have already found out, theta by 360 into 2 pi r, plus this linear distance PQ. Now to find out this linear distance, you look at a triangle POQ, which is an isosceles triangle with PO equals to OQ, both equal to the radius, and the angle which is there is theta. I can always find out the third side of the triangle by applying the sine rule, or I can look at one part of the triangle with this as 90 degree, the angle is theta by 2. I can apply sine theta. Sine theta, if I apply, sine is equal to perpendicular over hypotenuse. So in this, the perpendicular will be equal to I am talking about this angle, this theta by 2, perpendicular is the opposite side, which is PR, and hypotenuse is R. So, and this is sine theta by 2, because I am looking at one triangle. So, PR, if I have to find, would be R into sine theta by 2. Now, I want the total distance PQ, which is double. So, I will multiply this with 2 to get to my value. So, this is 2R into sine theta by 2. In order to find out the area of the segment of the segment of the circle, I will find out the area of the sector, which I have already calculated here, and subtract the area of triangle POQ from that. So this is the area of the sector, subtract the area of triangle. So I have the formula that I have applied is half AB sine C, half A, which is R, B, which is again R, sine of the angle between them. So this is sine of theta by this 2 that you have. Sorry, sine theta, and this 2 is for the total thing. It is half R1 into R into again sine of the angle between them. This is sine theta. This is not sine theta by 2, it is sine. This is sine theta by 2. The angle is half of the angle which is subtended at the center. 2 pi, as I already stated, is equal to 360 degree. Our pi is equal to, this 2 pi is in radian, and this 360 degree is the angle that you have in degrees. So radians can always be converted into degrees by following this rule. Let's look at the case of a circular ring. Circular ring is formed when you have two concentric circles. Concentric. Now concentric means they have the same center. Concentric circle means this O is the center of the smaller circle, and this O is the center of the bigger circle. Now the radius of the bigger is treated as capital R, and of the smaller would be written as small r. If I have to find the area of a circular ring or the perimeter of the circular ring, I will follow these formulas. For perimeter, if I look at the perimeter, it will be the length of boundary. I look at the circumference of the smaller circle, which is 2 pi r. I will look at the circumference of the bigger circle, which is 2 pi capital R. Now the total perimeter will actually be the sum of the two perimeters, because this is also the inner boundary and this one is the outer boundary. So total boundary is composed of inner plus outer. So I can take 2 pi common, and the formula that I will get would be r plus r. In order to find out the area, I will look at the area of the larger circle. From the area of the larger circle, if I subtract the area of the smaller circle, I'll get the area of the ring. So this will be pi capital R square minus pi small r square. Taking pi common, I get the formula capital R square minus small r square. So this is how I find the perimeter and the area of a circular ring. Circular ring is formed by two concentric circles whose radii have to be different. If the radii comes out to be same, it will not be a circular ring. It will be two circles which are on each other that you will get. Let's look at the next concept, which is the concept of a chord. Let's look at a circle. This is a circle which is there. If I join any 2 points on the circumference of the circle, I get a chord. Now the CD here comes out to be a chord. Another, any 2 points on the circumference of the circle joined with a line. This line is known as chord. So if I go by the definition, chord is the line which is joining the 2 points on the circumference of the circle. So these 2 points have to be definitely on the circumference of the circle. The point cannot be inside and cannot be outside. It has to be on the circumference of a circle. Since there are infinite number of points that you have on the circumference of the circle, there are infinite chords that you have for a circle. The number of chords would be countless. So any 2 points A and B on the circle, line joining them is known as a chord. Now if I talk about infinite number of chords, I can find out always which can be the largest chord. The largest chord would be the chord which are on the points which are far apart on the circumference of the circle, and these 2 points, if I join, the chord that I will get will definitely pass through the center of the circle and will be the diameter. So diameter is the longest chord of the circle that I have. I can find out the length of the largest chord, which is the diameter. Now let's look at some of the properties that I have for chord. Now if you have a chord AB and CD, which are equal in length, the angles that they will subtend at the center. How do they subtend the angle? You look at the 2 points AB which are at the circumference, which are the endpoints of the chord, join them with the center. So if I join these two with the center, this angle is the angle which is subtended by the chord at the center. Similarly, if I look at C and join it with the center, if I look at D, which is another endpoint of the chord, and join it with the center, this angle COD is the angle which is subtended at the center. So angle subtended at the center by equal chords is equal. So if 2 chords are of equal length, if 2 chords are of equal length, they will subtend equal angles at the center. So angle AOB and angle COD will turn out to be equal. In order to prove that, I can look at those 2 triangles and prove them to be congruent. How? I've already said that the chords are of equal length. So one side is same. What is this side? The radius. 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 So the 2 triangles become congruent with SSS rule. If the 2 triangles are congruent, the leftover angles would also be equal. So I get the 2 angles as equal. Note, they need not be the vertically opposite angles. So I will have the 2 things which are equal. Another thing I want to say is, before moving on to the next property of chord, I would like to say is, if there is a circle and if there is a chord, this is the angle which is subtended at the center. The longer the chord, the larger will be the angle subtended at the center. So I would say the length of the arc and the angle at the length of the chord, I should say. The length of the chord and the angle at the center are directly proportional. Angle subtended at the center is directly proportional to the length of the chord. So the longer the chord, the larger will be the angle subtended at the center. The shorter the chord, smaller will be the angle subtended at the center. So equal chords subtend equal angle at the center. That is what I want to say. Equal chords are equidistant from the center. So if 2 chords are of equal length, they have to be equidistant from the center. That is very, very obvious, because the shorter chord will be away from the center. The longer the chord is, the closer it will be to the center. So the longer the chord is, the closer it will be to the center. The longest chord passes through the center. The shorter the chord is, the far away it will be from the center. So I would say the distance from the center, and I am always talking about the perpendicular distance, is inversely proportional to the length of the chord. So the longer the length, the closer it is to the center, the shorter the chord, the farther it is from the center. And if two chords are equal, they have to be equidistant from the center and vice versa. So here, if you talk about this, the length of perpendicular distance would be equal. And also, if I talk about the length of this arc AB would also be equal to the length of the arc CD. OP is the perpendicular bisector of A. So the next thing is the line joining the center of the circle to the midpoint of the chord. So if I look at it, if I talk about this, this is the midpoint. The P point should be here. Line joining the center of the circle to the midpoint of the chord is perpendicular to the chord. OP, here P is the midpoint of the chord, is the perpendicular bisector of A. So if I look at the line which is joining the midpoint of the chord and the center, it is perpendicular. I can look at it vice versa. If I draw a line from the center to the chord, it will always be perpendicular to the chord and it will bisect the chord. If I need to prove this, I will look at the two right angle triangles that I have, which is ORA and ORB. These are the two things that I have. I can prove that the two triangles are congruent because this side will be equal to this side, this angle will be right angle, and this will be this thing. So I can say that AR and RB are equal. Similarly, if I assume AR and RB are equal, I can prove that OR is the perpendicular line to AB. So what I need to understand is, first, equal chords subtend equal angle at the center. Equal chords are equidistant from the center, and a line joining the midpoint of the chord to the center of the circle is always perpendicular to the chord, or a line drawn perpendicular from the center of the circle will always bisect the chord. Let's look at some more properties for chords. Now, here A and B are the 2 points that I have marked randomly on the circumference of the circle. If I join AB with a straight line, this straight line AB will be known as chord. If I join the two endpoints with the center of the circle, this will be the angle subtended at the center. Now, OA and OB will be equal because both will act as the radius of the circle. So, it will be an isosceles triangle that you have. The two endpoints of the chord can also be joined to any point on the circumference of the circle. Now, if I look at randomly 2-3 points on the circumference of the circle, let me take the points as X, Y and Z. I can join A with X and B with X. So, this will be the angle which is subtended by the chord AB at the circumference. This will also be the angle subtended by the chord at the circumference AB, only the same chord. This will also be the angle subtended by the chord AB at the circumference. So the rule is, angle in the same segment of the circle are equal. What does that mean? If a chord AB is there, it can subtend infinite angles in the same segment. Segment, if you remember, we have done major segment, major arc, minor arc. So this AB, I am talking here about the major one, the major, and this one is the minor that I get. So angle which is subtended in the major segment would all be equal by the same chord. Angles in the same segment of the circle by the same chord are all equal. So if this angle is theta, this will also be theta, and this angle will also be theta. And this angle which is subtended at the center is half the angle subtended at the center. So the angle which is subtended on the circumference would be half the angle subtended at the center. So this AB would be subtending an angle of 2 theta at the center and would be subtending an angle of theta at the circumference. Similarly, if I look at the minor segment, this angle, I'm not calling this as theta, let me call this as alpha, would be equal to the angle which is subtended by the same chord in the other segment. So in the minor segment, AB is subtending various angles at the circumference. All these angles would be treated as alpha and all of these angles would be equal. Theta, however, would not be equal to alpha. If I just extend this theorem also, the angle subtended at the center has to be twice the angle subtended at the circumference. So the angle which is subtended by the minor thing AB at the center would be this angle that I'll have. So if I look at it, I can find out the relationship between theta and alpha. Theta and alpha would sum up to 180 degree, because if you look at 2 theta is the angle subtended at the center in the major arc and 2 alpha is the angle which is subtended at the center by the minor one. This has to be 360 degree because it is the total angle which is there at the center. So I can get theta plus alpha is equal to 180 degree that I have. So I'll have the angle that are subtended are 180 degrees. So AXB plus APB, which is the angle subtended in the major and in the minor. One angle is in the major, another one is in the minor. They are always supplementary. The angles which they form in the two segments are always supplementary. So let's look at the property that I have. If a line segment joining 2 points subtends equal angle at the 2 other points lying on the same side of the line containing the line segment, the 4 points lie on the circle. That means the 4 points would be concyclic. So what I'm trying to say here is, if you have 2 points and there's a line segment which is basically the chord which is joining the 2 line segments, such as what? Such as AB. It subtends equal angles at 2 points lying on the same side of the line. So I'm talking about this angle theta, this angle y, and same side. Then the 4 points that you have, 4 points that I'm talking about is A, X, Y and B, would turn out to be actually concyclic points. These 4 points would lie on the circumference of a circle. The next property that we need to remember for chord is angle formed in a semicircle is 90 degree. What I am looking at, AB is the chord and it is actually also the diameter. The diameter subtends an angle of 180 degree at the center. So the angle subtended by it at the circumference is half the angle subtended at the center. So if at the center the angle is 90 degree, 180, the angle at the circumference would always be 90 degree. So if you have a right angle triangle inside a circle, that will always be a case where the third side would act as the diameter. A diameter always makes an angle of 90 degree because the angle at the center is 180 and the angle at the circumference is half the angle at the circumference. So if you look at it, D would be equal to 90 degree, angle AEB, the angle which is formed inside, this E point is not on the circumference, would be greater than 90 degree, and the angle which is formed outside the circle would be less than 90 degree that I have. Now the next concept is the concept of cyclic quadrilateral. If you have gone through our presentation on quadrilaterals, you would have already covered this. So a quadrilateral whose all the 4 vertices lie on the circumference of a circle is known as a cyclic quadrilateral. I have a quadrilateral, so all the 4 vertices A, B, C, D lie on the circumference would be known as cyclic quadrilateral. Here, if you look at the 4 sides of quadrilateral AB, BC, CD and DA actually act as chord. Now I'll be looking at cyclic quadrilateral from the point of view of chords. So this AD is a chord that I have. If I look at it, AD is subtending an angle ABD at the circumference. This AD same chord is subtending an angle which is ACD. These 2 angles would be equal. If I look at the chord DC, DC is subtending this angle. Let me use with a different mark at the circumference. This DC is subtending this angle at the circumference also. So these two angles would also be equal. Let me call this as Y and let me call this as Y. If I look at a chord BC, BC is subtending this Z angle at the circumference and BC is also subtending Z angle at the circumference. These two angles would be equal. The fourth one, if I look at it, is AB. AB subtending an angle ABD, which let me call it as theta, and AB is also subtending an angle which is ACB at the circumference. The angles subtended in the same segment are equal. So all the angles that I have marked comes out to be equal in this case. And I also know angle subtended at the circumference is half the angle subtended at the center. So if the angle at the circumference is x, this angle would be 2x. If the angle at the circumference here is y, this angle would be 2y. If the angle at the circumference with the, let me call this thing as the theta 1, theta, this angle would be 2 theta. Similarly, what I am left with, if the angle is, this angle is z, this angle will be 2z. So if I look at it, 2y plus 2x plus 2 theta plus 2z is equal to 360 degree. So x plus y plus z plus theta would be equal to 180 degree that I have. So if I just look at it and if I combine the thing x plus z and y plus theta, if I just combine this, this is the total angle x plus z, this is the total angle y plus theta that I have. What I get is sum of opposite angles in a cyclic quadrilateral is 180 degree. Though I've already learned the property, this is how we prove this. Now all the 4 points will be concyclic points, and angle A and C, which is the sum of opposite angles, and angle B and C, I've already proven the same by using the properties of chord, sum up to 180 degrees. The other property is exterior angle of a cyclic quadrilateral is equal to the opposite interior angle. So this exterior angle that I have will be equal to the opposite interior angle. So angle C, it will be equal to angle A. So if you look at it, we have already proven that y plus theta is equal to x plus z. So if I replace y plus theta with an exterior angle C, so I can say this angle is 180 degree minus C. 180 would get cancelled out, C would go to that side, and I will get this property. The other thing that you need to remember when you're talking about the case of cyclic quadrilateral is Ptolemy's theorem. The theorem is sum of product of opposite sides is equal to the product of the diagonals. So if you take the opposite sides AB and CD, multiply them, add it to the other product of the opposite side, which is BC and AD. If you will look at the right hand side, it will be equal to the product of the two diagonals that you have. Very important theorem, can only be applied to the case of cyclic quadrilaterals. In order to find out the area of a cyclic quadrilateral, I would look at the Heron's formula and extend it. So the formula that I will get would be S minus A, S minus B, S minus C, S minus D, where A, B, C, D are the four sides of a cyclic quadrilateral and S is the semi-perimeter. So this can only be applied if I know all the lengths of the four sides of a cyclic quadrilateral. If a cyclic quadrilateral is a parallelogram and it has to be inside a circle, then the only case that it can be is the case of either a rectangle or a square. A parallelogram inside a circle becomes a rectangle and a square, or a square I should say, and the diameter of the circle act as the diagonal of a rectangle or square. In general, we'll take it as a case of rectangle. It may come out to be square as well, but we'll start with the case of rectangle only. Now let's look at the second thing, which is a secant. So I've already understood chords. Look at the figure 2 that I have. Here A, B and C, D are the two chords of the circle which are intersecting at a point P. Now this P point is the point of intersection of the two chords that you have. Whenever two chords intersect inside the circle, I can follow the property which is PA into PB, which is the distance of this point from the 2 points on the circumference of the circle. So it will be PA into PB is equal to PD into PC. So you will have PA into PB is equal to PC into PT. Now, in order to prove this, you can you can look at the chords. You can join the 2 points and can form the chords, and the 2 triangles that you will get, which will be this triangle and this triangle, would become similar. You will need to prove that the 2 triangles are similar. That means the angles are equal. You will just prove that the angles are equal. Once you get the angles are equal, the 2 triangles are similar, their corresponding sides would be proportional. So if I just look at this thing, I can prove that the triangles are congruent. These 2 triangles are congruent. If I take, let me just change the color and explain you with the, if I just join PD, if I just join BD, if I join BD, this is not getting right. Let me just erase this and draw it again. So if I just join this, if I just join AC instead of BD now, and I join these 2, these are the 2 triangles that I have to prove that they are congruent. So if I look at this chord AC is making this angle at the circumference. This chord AC only is making this angle at the circumference. So these 2 angles have to be equal. Similarly, if I look at the other thing that I have, if I look at this chord BD. Now this chord BD, BD is subtending this angle at the circumference, and BD is subtending this angle at the circumference. So these 2 angles would also be equal, which is the angle subtended by the same chord in the same segment. The third set of angles would obviously be equal because they are vertically opposite angle. So if I look at it, triangle CPB will become similar to triangle APD. So once the triangles are similar, their corresponding sides are proportional. I can take the ratio of their corresponding sides and I can get this equality. So if I just take these 2 sides, so if I take first this angle, it will be PB, and the corresponding angle which is equal here, which is PD, is equal to, I am talking about now this angle, which will be PC in the bigger one, and in the smaller one it will come out to be PA. So I'll just multiply them. I get PB into PA is equal to PD into PC. That is the property that I have. The same property can be extended to secants. Now what is a secant? AB is a chord. If I extend the chord, that extended chord is known as secants. So if you look at AB and CD are the 2 chords which are not intersecting outside the circle, inside the circle. However, once extended, they intersect outside the circle at the point P. Here, AP and PC will be known as secants of the circle. The property that we have applied to chords can also be extended to secants. The properties from the point of intersection move to the 2 points on the circumference of the circle. So it will be PB into PA equals to PD into PC. The proof of the same can also be given with the help of similar triangles. So if I just join these 2, I can prove that the smaller triangle and the bigger triangle would come out to be similar, and I can take the ratio of their corresponding sides and get this result. This result is very, very important result that can be applied when chords are intersecting inside or outside the circle. Now let's look at a tangent. What is a tangent? A tangent, if you look at this figure PT, a tangent is a line which touches the circle at only one point. It does not intersect the circle, it is not inside the circle, it is only touching the circle at one point. This one point here is represented by the point T. So PT is a tangent that I have, and the tangent is always perpendicular to the circle at the point of contact. So this is the point of contact. PT will be perpendicular to the circle. When I say perpendicular to the circle, I actually means if I join this point with the center of the circle, it will be perpendicular to this circle. So a line from the center of the circle with the point of contact is always perpendicular to the tangent at the point of contact is what you have. So the two things that I need to remember is tangent touches the circle at only one point, and at that point it is perpendicular to the circle. The next thing, from any given point I can only draw two tangents to the circle. So from a given point P, I can only draw two tangents, which is PT and PT dash, to the circle. I cannot draw a third tangent. Third tangent would either be inside, if I try to draw, would pass through the circle, or it will be outside the circle. It will not be able to touch the circle. And the length of these two tangents from the same external point is equal. So PT and PT dash, from an external point, the two tangents that you can draw are equal in length. The property that we have looked at in the case of chords and secants can also be applied to the case of tangents. So this is one tangent which is intersecting with a secant AP. Again, from the point of intersection, look at the 2 points on the circumference of the circle. So PA into PB is equal to PT. I don't have another point, so I'll again do PT. So PA into PB is equal to PT square. That is the rule that we have when I'll have to apply it to a secant and a tangent. Now let's look at the case of common tangents. If you have two circles which are not joining, or which are not touching, which are not intersecting, you can have a pair of tangents which can be tangents simultaneously to both the circles. So here, if I look at it, if I look at PQ and RS, they are known as direct common tangents. Common tangents because they are common tangents to both the circles, and direct because they do not intersect. They are direct tangents, that means they are not intersecting each other. This distance PQ is known as the length of the common tangent. This is the length of the common tangent that I have in this case. Now, if I look at the direct common tangent, which is PQ and RS, their length would be same. So that means if I find out the length of PQ, that same will be the length of RS. So if I find PQ or RS, they'll turn out to be same. So I'll find out the length of 1. If I join O1 and O2, this line will be known as the distance between their centers. Distance between the centers that I have. This O1P is the radius of the first. O2Q is the radius of the second. Now here I am imagining that R1 is greater than R2. So O1P would be greater than O2Q that I have. In order to find out the length, what I will do is, I will draw a line parallel to PQ passing through, starting from O2. So if I just draw a line parallel to PQ passing through O2, I'll get a line like this. Now if this was R2, this distance would also come out to be equal to R2. I will look at the leftover triangle that I have. This smaller triangle that I am left with is what I will look at. If I look at this O1 O2 will be, I'll just try to make this triangle here. This O1 O2 will be the line joining their centers, or the distance between their centers. This length will be equal to R1 minus R2, because this will be actually equal to the distance between the two radii. For R2, I've already drawn a line parallel, so this distance I'm left with is R1 and R2. And I join this I've drawn parallel to PQ. So if I just join this will be basically the length of the common tangent. Now the point to note here is, I've drawn this line parallel to PQ and equal to PQ. So the angle which is a right angle here will also be a right angle here, though it doesn't look like in the figure, but it is a right angle there. So the first thing that I need to remember is the distance between their centers is always greater, because it will be a hypotenuse, will be greater than the length of the common tangent. The length of the common tangent would be less than the distance between their centers. So I can apply Pythagoras theorem. The distance between their centers, which is O1 O2 whole square, is equal to the length of the common tangent square plus the difference between the two radii. So this will be the hypotenuse, this will be the perpendicular, and this will be the base. So base square plus perpendicular square is equal to hypotenuse. Since I have to find the length, I will do hypotenuse square minus perpendicular square as the square of the common tangent. So it's just a simple Pythagoras theorem that I need to apply to find out the length of the common tangent. Other way the common tangents could be is transverse common tangent. Direct common tangent do not intersect, whereas transverse common tangent, if I look at PQ, if I join, this is a tangent to circle 1, this is a circle tangent to circle 2. Similarly, R and S, join them. This is a tangent to circle 1 and this is a tangent to circle 2. Both the tangents, they intersect at a point which is S. Such tangents will be known as transverse common tangents, and the length of this pair would be equal. So that means whatever is the length of the first tangent would be equal to the length of the second tangent that I have. So the length of PQ will be equal to the length of RS. In order to find out this length, I will look at these two triangles and use Pythagoras theorem to solve it out. Now if I look at these two triangles, this is the case of vertically opposite angles that I have. This angle, I know that the tangent is perpendicular to the circle at the point of contact, would be 90 degree. So by double A rule, the two triangles would become similar. So this triangle and this triangle would become similar, and I can say that the other sides are proportional. So I can look at the thing and I can say whatever is the ratio of R1 over R2, that same will be the ratio of O1H over O2H. So that means the line joining their centers is divided in the same ratio as the ratio of their radii. Or I can write this is also equal to PH over HQ. The common tangent is also divided, the length of the common tangent is also divided in the ratio of their radiuses. So if the radiuses are given, I can find out the length of their line joining their centers, and I can find out the length of O1H and O2H. Then apply Pythagoras separately in both of these triangles and find out the length of PH and HQ. Add them up to find out the length of PQ. So once I understand this, I will apply Pythagoras in this triangle, find out the length of PH. I'll apply Pythagoras here, I'll find out the length of HQ, add them to get to PQ. Or I can apply the direct formula, which is the distance between their centers, square of that minus. Now instead of using R1 minus R2, which was the case in the first case, I would do R1 plus R2 whole square. This would give me the length of the common transverse tangent that I have. So if you look here, in the previous case, I was just subtracting R1 minus R2. Here I am subtracting R1 plus R2. So the length of the transverse common tangent would be less than the length of the direct common tangent, because I am subtracting a greater part. There I was subtracting minus, here I was subtracting plus. I am subtracting a larger portion, so the length of transverse common tangent would always be less than the length of the direct common tangent. Let's look at the case. Here I will just say PQ and RS and the lengths are equal. PQ will be equal to RS will be the case of direct common tangent that I have, and their lengths would be given by O1 O2 whole square, which is the line joining their centers, minus R1 minus R2 whole square, which is the difference of their radii. And AB is a transverse common tangent. Now I cannot find out the length of AB because AB is a tangent at this common point, and the two circles here, the two circles here touch each other. They do not, in the previous cases that we have done, the circles are not touching each other. Here the circles are touching each other, and the line joining their centers would be actually equal to the sum of the two radii. So the line joining their centers is actually the sum of the two radii that I have. So the length of PQ and RS would be less than the distance between their centers, would be less than the sum of the two radii. Let's look at another case. When the two circles are intersecting, now if the two circles are intersecting, again I can find out PQ and RS. They are the length of the direct common tangents that I have. In this case, I will not be able to find out the length of the transverse common tangent because the circles are cutting each other, or they are overlapping. Here, the distance between their centers would be O1 and O2 would be less than. This will be R1, this will be R2. This will be the common region that will be there, would be less than the sum of the two radii, because there is an overlapping region which is counted in R1 and R2. So I'll have to subtract that overlapping region. If one circle is completely inside the other circle and touching the other circle. So let's look at this case. So this smaller one is inside the bigger one. AB is the common tangent that I have, is only the common tangent that I have. And the distance between their centers, if you find out, will actually be the difference of the two radii. This is totally R1, which is I'll call, this is R2. So the distance between their centers is the difference of the two radii that I have. A circle completely inside the other with no part being touched with the outer one. I'll have no common tangent at all, and the distance between their centers would be less than the difference of the two radii. So this total is R1. This total, if you look at this total, is R1. If I subtract R2 also, this is the distance between their centers that I have. This is actually less than the difference of R1 minus R2. The next thing that we'll discuss in the case of circles is an alternate segment theorem. This theorem says the angle between a chord passing through the tangent point and the tangent is equal to the angle subtended by a chord to any point on the other side of the circumference. Let me explain you with the help of an example here. So CB here is a chord to the circle that I have, and PQ is a tangent. The angle between the chord and the tangent, this is the angle which is formed between the chord and the tangent, will be equal to the angle which this chord makes in the alternate segment. So this chord on the circumference makes an angle CAB. This is the minor thing. I will look at the angle which is made in an alternate segment. These two angles would be equal. The angle made by the chord with the tangent is equal to the angle which the chord makes in the alternate segment. Similarly, if I talk about AB as the chord, AB makes an angle, this angle, with the tangent. AB also makes this angle at the alternate segment. So this angle would be equal to the angle that it will make in the alternate segment. So angle CBQ will be equal to angle BAC, and angle ABP will be equal to angle BCA. Thank you so much for being with us. For practice question, you can refer to our website edusathi.com.